Now let us look at the examples of Bayesian equilibrium in the Bayesian games. So let us get back to the previous example of a sealed bid auction. The problem setting is the sealed bid auction. We know that in this example there are two players who are willing to buy an object, and their values and bids lie in this set 0, 1. And the allocation is very simple. If player 1 bids at least as much as player 2, then the object goes to him, otherwise it goes to player 2. And the common prior is uniform, and they are also independent in this case. So in this setup, we will consider two kinds of auctions. So the first auction is called the first price auction. This is the kind of auction that we are most familiar with, or maybe can relate to it most obviously. So here, if player 1 wins, then he has to pay the amount he or she has bid for. And similarly, player 2, if it wins, then it has to pay whatever it has bid for. So every player, the winner pays his bid. That is the one-line description for first price auction. So you can write the utility in that context as what we have written in the previous case. The type determines how much they value that object, and the bid, because they are paying their bid at the when they are the winner. So this difference is the net utility when they are the winner. So this happens for player 1 under this condition, and for player 2 under this condition. Okay, so now we can think of that the bid is actually the strategy of player I. We can think of that to be a function. So here we are only discussing about the pure strategies. So a pure strategy of player 1 is a function that maps this theta i's, theta 1's into the strategy space, which is again between 0 and 1. So the action space for both these players again is this closed interval 0, 1. 0, 1, that is going to be the action space for both these players, and the theta i's are also living in the same space. So for simplicity, let us assume, so let's say it is a fraction. So alpha I is some positive number which could be a fraction, of course less than 1. Nobody will bid more than his own value. Whatever he is going to bid is represented by this fraction alpha of I. Right? That is the strategy for every player. Now let us find out what is the Bayesian equilibrium. So in this context, we need to find the SI star, or equivalently what we are trying to find is alpha I star, that maximizes the X interim utility for player I. So this is the problem that each of these players are trying to solve. Now you can write this down. This is very simple. The X ante the X interim utility can be written down explicitly, and let us read it in the following way. So this was the utility, the same utility expression that we have already written, and now we also know that player 1 has actually observed his own theta I. So player 1 knows what theta 1 is. Depending on that, what is the probability that theta 2 will be so theta 2's distribution it can find out. Of course it is an independent distribution, so therefore it will be the same. Now how is that theta 2 appearing in its own utility expression? It is appearing here. So it wins, player 1 wins only when this bid B1 is at least as much as the strategy, the bid that has been chosen by player 2, and this is exactly B of 2. So here it appears, so it does not exactly know what player 2 has bid, but it knows that it is some fraction of that theta 2. So it can now calculate this value, and it turns out that so you can actually do this maximization only between 0 and alpha 2. What is the reason? Because B1 never needs to bid any larger than alpha 2. That is because theta 2 is always living between 0 and 1. Therefore, if you take the value anything larger than alpha 2, that really has no meaning, because player 2's bid will never go beyond alpha 2. So this maximization problem is between 0 and alpha 2, and in that space you can do this integration and find out that this is the value for that. So b1 star, if you want to find the maxima, so of course this is maxima over a restricted interval. So it will have the following values if b1 star will be equal to theta 1 by 2 if alpha 2 is greater than this alpha theta 1 by 2. This is one condition. I mean, you just need to work this out. Otherwise it will be alpha 2. So essentially it is taking the minimum of both these two things. So the optimal strategy for player 1 under this setting, what we have defined, is going to be the minimum of theta 1 by 2 and alpha of 2. And similarly S2 star, in a very similar way, you can find that this is going to be theta 2 by 2, the minimum of theta 2 by 2 and alpha of 1. Now one specific solution where you can think of this as one of them. So notice that if you pick both this alpha 1 and alpha 2 to be equal to half, then using the fact that this theta 1 is always between 0 and 1, it will be always less than equal to 1. Therefore this minima will always emerge as the theta 1 by 2. So that is one candidate Bayesian equilibrium, of course. Right? So this essentially says that in the Bayesian game that is induced by this uniform prior, we have assumed, on first price auction, bidding half the true value is a Bayesian equilibrium for both these players. Right? So this is a best response for both these players, and on a different level you can also think about it. Whenever some agents in the first price auction, whenever the player is bidding, it has to be careful because if it becomes the winner, then it has to pay the same bid. So therefore, whether it should, so one clear thing is that it should not bid the value itself, their true theta 1s, theta i's, because then in that case, even if it wins, it has to pay the whole amount. So its net payoff would be 0. While here it at least has theta 1 by 2 as a net payoff. So this is one example of the Bayesian equilibrium when you are talking about the first price auction. Now let us look at a variation of the same problem. So now the winner determination rule remains the same. Still the highest bidder wins, but the payment rule is different. It pays the second highest bid. So when there are only two players, if player 1 wins, it pays the bid that has been given by the player 2. Right? So what happens is the utility changes. The winner determination is still the same. Player 1 will win if b1 is at least as much as b2, but the net payoff will change from theta 1 minus b1 to theta 1 minus b2, because this is the other player's bid that it is expected to pay. And similarly, when player 2 wins, it should pay the bid of player 1. So now we can actually do a very similar exercise of finding what is the solution of this bidding problem. Now we'll have to replace this part with the strategy of player 2, and we know that can be replaced by alpha 2 theta 2, and this winning condition will also be dependent on theta 2. Now this problem can be solved, so you can take this integration and solve this integration to find out what is the so notice that here theta 1 is a fixed constant, because for player 1 it already knows what theta 1 is. What is unknown, or the random variable, is this theta 2. So therefore everywhere we are integrating with respect to the theta 2, not theta 1. And now if you look at the final expression for utility for player 1, you can see that this expression is going to get maximized when b1 is actually equal to theta 1. So similarly you can find out b2 equal to theta 2. So which means that in the context of second price auction, in the Bayesian equilibrium of the uniform prior, the bid, the Bayesian equilibrium should be when the player bids its valuation itself. Now this is not only limited to the uniform prior, actually it can be made more general, if these distributions of theta 1 and theta 2, these two things are arbitrary but independent, as long as they are independent, the maximization problem, you can just work that out. It will change a little bit. Instead of that to uniform probability distribution, this will now have a arbitrary probability distribution, so which is given by the CDF of capital F, and you can write this down. And now the problem for player 1 is to solve this expression with respect to B1, and then again you can do the differentiation and find out that B1 will be equal to theta 1. So that is the optimal solution of this utility. So utility will get maximized. Of course, in both these examples I have just taken the first order condition, but you can check the second order condition. It will be negative, therefore it is going to get maximized. And as long as this probability masses are positive, so summarizing these two things, we can say that for any independent positive prior, so this part is actually crucial, we need the positive prior, bidding the true type is a Bayesian equilibrium of this induced Bayesian game in the second price auction. So that is something that we didn't see in the context of first price auction. So essentially what is happening in the second price auction is that the players are never asked to pay their own bid. They know that even if they win, they are always going to pay the second highest bid. So therefore it gives a certain kind of incentive to actually reveal their types truthfully. We will actually see this more when we discuss mechanism design.